Firstly, we have the number 1. That is this problem. It says, an object is dropped from rest on X and slide to Y. The vertical distance between X and Y is 10 meters. During motion, 20% of the initial gravitational energy is lost by friction. And we have 4 answers. That is this one, and this one. So first we need to know that the initial energy is the same as the final energy plus the frictional energy that we lost, okay? So we have to answer for B. That is going to be what we are looking for. The first thing that we can do is cancel the m's. So it says like GH is equal to 2b squared plus GH. Perfect? And so this is a number. We can pass it subtracting. So it would be GH minus 0.2 GH is equal to 1/2 of b squared. Okay? So this can be subtracted and it's going to be 0.8 GH is equal to 1/2 b squared. We pass this multiplying, so it's 1.6 GH is equal to b squared. Root in both ways, and we have root of 1.6 GH is equal to b. So this can be expanded, and this is going to be equal to 1.6 times g times 10, because it's the height of the initial volume. Perfect? Perfect. So this is equal to b. This and this can be multiplied, so it's going to be 16g root is equal to b. And this can be divided, so it's root of 16 times root of g times root of g is equal to b. This is 4. 4 root of g is equal to b. So we know that our answer is letter C. 4 root of g.
Bueno, pero no te ríes. Bueno.
Okay, now we are going to do the question 2. We have these units. We have K, the constant sprint. We know that the extension is from 3 centimeters to 5 centimeters, and we need to calculate the work. First, we need to do a conversion. We can't work with centimeters, so we need to put it in meters. So 3 centimeters is equal to 0.03 meters, and is 0.05 meters. So we know that the change in energy is final minus initial, and this is equal to the work done. So final minus initial is 1 of k x constant. This is initial. No, this is the number 2 because this is the final. And then 1, the k is constant, so we are not going to change it. And this is equal to work. So if we do this, is 200, and this is 0.03. No, 0.5. Sorry, 0.5 minus 200, and now yes, 0.03, and work. We can't cancel this. Well, not cancel, but just put like 100, and then square. And this is and then let me do. So after we did some math with the calculator, and 0.25 minus 0.09 is equal to 0.16. And some common error is that you don't convert the centimeters to meters, so it's going to be like 1,000, but it's not correct because all units need to be in meters instead of centimeters. Another thing that you can be wrong is to put initial minus final. This can be like minus, but it's not because it's final minus initial. And always remember that the work is equal to the change in energy. Yeah. Okay, now we are facing the number 3 question, and it tells us to calculate the friction force. We have the mass, we have the displacement, the initial and final velocity. The final velocity says arrest, but it's also equal to 0, no? So first, to calculate friction force, we need to also remember that work is equal to Fs cos of 180. Why 180? Because this angle is 180, because the friction is opposing to the dragging force. So 180 is equal to minus 1. So work is equal to Fs. And we know that Fs is equal to 4. So work is equal to F4. Right here we have two variables that we don't know, but we can know the work. Why? Because work is equal to change in energy, and our change in energy is equal to final minus initial. The final is going to be 0 because the block stopped, and the initial is going to be 1/2 of mv squared, that is equal to 1/2 of 2 and 5.4 squared. So to rewrite all is 1/2 of 2, 5.4 squared is equal to F4. And to this, to have the F alone, we only need to do some math. And this is our friction force. And let me do the thing. Espérame. Okay, now so then we have that 7.29 is equal to F, but due to significant figures, F is equal to 7.3. And also remember to put the units. Since it's frictional force, we're going to put newtons. So this is our final answer due to the significant figures, and that's all. One thing that you can be wrong about is to not remember that work is equal to change in energy, and also the angle. The angle change.
So, the fourth question says, the graph shows the variation of force on an object versus the distance it moved. The object is initially at rest and moves 50 meters horizontal distance. So the first thing that we need to get is the work done in these three triangles. How do we do that? First, in the graph we saw that this has a distance, a base of 5. Our base is equal to 5, while the height is equal to 80. So 80 is equal to h. And we have the formula of the triangle. Triangle area is equal to 1/2 of the base times the height. And we have three triangles that are exactly equal. So forget the total area of the triangles is equal to 3 times 1/2 of the base times the height. And this is equal to base 3, 1/2 of 5 times 80. And all of this is equal to 60 joules. But there is a friction that is opposing the movement. That friction is equal to 2n. So with the formula of work is equal to Fs cosine of the angle, we can put these values. The work done by friction is equal to the friction, that is 2n, times the displacement, that is 50, and it's opposing movement, so this is going to be cosine of 180. So we have that the work done by friction is equal to 2n 50 minus 1, and this is going to be equal to minus 100 joules. Perfect. So we have, this is our area, and this is the value of the friction. So for getting the total work, we have to subtract it. Work total is equal to 60 joules minus 100 joules. So work total is equal to 500 joules. That means that our correct answer is B.
Okay, now so in question number 5, we have this scenario. We have a ball that bounces on a vertical wall, and we know that it's a laser collision. So our question is, what is equal to 0? And these are the options that we have. So first, we can say that B is not, because the impulse doesn't add to 0. And then the rate of change of linear momentum also is not equal to 0, because the rate of change is not, if you sum it, is not 0. Then the magnitude of change of linear momentum is also not 0. Why? Because we can say that magnitude, it doubles down. Like if this is 10 meters per second and it rebounds, the velocity is negative, so the velocity is at to zero, but the magnitude, it doubles down. The magnitude right now is 20. So finally, the only answer we have that is the correct one is the change of magnitude or linear momentum, because even if you put in here and in here, the velocity are obviously different, because one is on left and one is on right. But if you add these magnitudes, it cancels out each other, and this is the correct one.
So let's move to the sixth problem. This says a projectile is launched upwards at an angle theta to the horizontal with an initial momentum of P0 and an initial energy of S0. Every resistance is negligible. What are the momentum and total energy of the projectile at the highest point of the motion? We know by definition that the energy is conserved. The energy final is equal to the energy initial. Why? Because there are no external forces that affect our energy. It's only changing from kinetic to gravitational. Okay? So we could say that the A and B that the energy conserves are the correct answers, while the C and D, where the energy is not conserved, are incorrect. Okay. Zero. So we have to focus only in these two. We need to know if momentum is conserved. Momentum is conserved in this situation. The answer is no. That is mainly caused by the change in magnitude. In this point is different than in this point. The velocity in this has an angle. Let's say that is velocity cosine of the angle times velocity sine of the angle. While in this part, velocity is full cosine of the angle. There are no other value of velocity that we need to know. So the velocity is not conserved. Let's say that here we have an angle of 30 degrees and an initial velocity of 5. For this, it's going to be 5 cosine of the angle and 5 sine of the angle. This is our initial velocity, while in this part is only b cosine of the angle. There are no change. So knowing that, we know that the momentum changes. So this must be our correct answer.
To problem 1, we got the problem that it says a ball of mass 0.8 kilograms is attached to a string. The distance to the center of the mass of the ball from the point is 95 centimeters. The ball is released from rest when the string is horizontal. When the string becomes vertical, the ball collides with a block of mass 2.4 kilograms that is at rest in a horizontal surface. And the first question asks, right before collision, show that the speed of the ball is about 4.3 meters per second. So first what we need to do is make these 2 meters, as well as that is like the main unit for this kind of exercises. So 95 centimeters is the same as 0.95 meters. With this in mind, we can now move on to the comparison of to the conservation of energy. So we have point A and point B. Point A at max height, where we have potential gravitational energy, MGH, And in point B, we have kinetic energy, which is 1/2 of mv squared. So we know by law of conservation that this has to be the same as this one. So we just make them equal, and mvh equals 1/2 of mv squared. We can cancel mass, and we end up with vh equals 1/2 of v squared. Now we solve for velocity as we want this value, and we end up with root of 2gh equals v. Okay, so now we can put 2 times 9.81 times our height, which is the same as the length of the string. So it's 0.95. And with a quick calculus, we end up with 4.3173, which is similar to 4.3 meters per second. So let's move on to problem B. In this case, it tells us after the collision, the ball rebounds and the block moves with speed. So let's say with speed 2.16 meters per second. Show that the collision is elastic. So we have like this. We know that the this square moves along our path. So now we want to prove that it is elastic. So in an elastic collision, we know that when an object A collides with an object B, so it's elastic. We know that this is the before and the after, which in this case will be going on opposite directions. So what we know about this problem is that momentum and energy are conserved. So with this in mind, we can do, and we know that momentum equals mass times velocity. And now finally with this in mind, we can do a sum of the before and the after, and this must be equal, which in this case will be m1 m1 plus m2b2 equals m1 b3 plus m2 b4 sorry. Okay, so putting this into our problem, we know that this square is at rest, so it means that its velocity is 0, and this will be our mass too. So in our formula, as m2 multiplies 0, we can cancel this, and then we end up with m1 v1 equals m1 v3 plus m2 v4. So after this, we end up with m1 velocity 1 equals m1 velocity 3 plus m2 velocity 4. Now the problem gives us that velocity 4, which is when it moves, will be about 2.16 meters per second. So we need to substitute for velocity 3, sorry. So we have 0.8 times our previous velocity, 4.3 equals 0.8 v3 plus 0.4 times 2.60. Okay, so now we solve for v3. 0.8 times 4.3. This one goes to the other side, subtracting 2.16, and this is equal to 0.833. And this mass will go dividing, ending up with 3 is equal to everything. So now let's put this in the calculator, and we end up with V3 equals minus 2.18. Okay, so after this, we got another piece of data for an elastic collision, which is that the energy from the beginning will be the same as the end. So the before is 1/2 of m1b squared, and of course that we know that object b, which is in the box, has velocity 0, so this will be plus 0. And we have the objects. 1/2 of m2b, m1 base 3 plus 1/2 of m2b4. Okay. So now we make them equal. And now we substitute. In this case, to prove that our phase statement is that after the collision, the ball rebounds. Show that the collision is elastic, and to show that it is elastic, we need to prove that this is equal to this. So after a quick substitution, we have 0.8 times 4.3 squared is equal to 1/2 of 0.8 times our previous velocity that we got here. Squared plus 1/2 of 2.4 times 2.16 squared. So with a quick calculus again, this is 7.36. This is, which is a close approximation. So we'll say that it's it.
So for the second exercise of section 2, it says 2 players are playing table tennis. Player A hits the ball at a height of 0.24 meters above the edge of the table, measured from the top of the table to the bottom of the ball. The initial speed of the ball is 12 meters per second horizontally. Assume the air resistance is negligible. So that's like the context of the problem. And then it says the ball bounces and reaches a peak height of 0.18 meters above the table with a horizontal speed of 10.5 meters per second. The mass of the ball is 2.7 grams. Determine the kinetic energy of the ball immediately after the bounce. This is the first part of this exercise. So we know that the only thing we're going to care about is after the bounce. And it says that here its max height is going to be 0.18 meters. And its horizontal speed is 10.5 meters per second. So we know that the energy here, the kinetic energy here and the kinetic energy here, it's going to be the same. So we know that kinetic energy of A is equal to, well, to kinetic energy of B. So for kinetic energy of B, we know that here we have potential kinetic energy and kinetic energy. So we're going to do the math. Okay, so for potential energy, it's mass times gravity times height plus 1/2 the mass velocity square. So we know that the mass it's 2.7 grams, but we have to work with kilograms. So it's 2.7 into. There we go. Okay. Kilograms. So it's 0.0027 times 9.81, and the height that the bounce reached 0.18 plus 1/2 the mass 0.0027 and its velocity squared. So we're going to plug all of that into our calculator, and we are going to get 0.1536. And that's it for the first part.
Now let's move on to the next exercise. Well, my partner previously told you about this ball that bounces on the table and then is hit by a tennis player with this paddle. It's completely vertical. My drawing is not completely vertical, but I didn't want to draw it again. What does the problem say? The problem says that the ball is going at 10.5 meters per second. The collision is completely elastic and it takes 0.010 seconds. We know that the mass, that the ball's mass is about 0.0027 kilograms, and that's it. We need to get the. What do we need to get? We need to get the force that the paddle is applying to the ball. Look at this beautiful ball. Okay. Then, how are we gonna find out the force? It's here. Okay, now. We gotta use this formula that states that the force is equal to the change in change in momentum. I was nearly wrong. Over the change in time. As the time we already have in that format, it will be just time, okay? Then the momentum, the change in momentum can be represented as final momentum minus initial momentum. How come? Because delta means change, and change means final minus initial. Okay. This can be transformed into, well, substitute by mass times velocity, final mass times velocity minus the same initial over time. We can factorize the m.
And as a consequence, as the is an elastic, we know that it's going to be exactly the same, however, with the sign change. So it's going to be minus mv minus mv. That this can be written as minus 2 mv over time.
What my partner clearly do, as this paddle is completely vertical and the collision is completely elastic, the ball will impact the paddle at the exact same magnitude of velocity, then it leaves the paddle. That's why it's the same value here. This minus is because this is in the opposite direction, and this, yeah, opposite direction, and the other minus is due to the formula. Then this is minus mv, it's minus 2 mv. Absolute math.
Yep.
Okay, we're gonna compute minus 2 times 0.0 this and this times all we just did in the board, but now in the calculator because we want to calculate it. Oh shit. Okay, minus 5.67. Okay, and that is our result.
So exercise 3 says a body of mass of 4.2 kilograms with initial speed of 5.6 begins to move up an incline as shown. The body will momentarily brought to rest after colliding with a spring constant of 2020. The body stops a vertical distance of 0.85 meters above its initial position. So first question is, determine the amount by which the spring has been compressed. There are no frictional forces. So this means that energy will be conserved. So if we start from here, it's gonna look like this. But we want to know the x, so which is the distance. So we're gonna rest this. So it's gonna be something like this times 5.6 squared minus 4.2 times 9.81 times 0.85. So this should be about should be something like this: 65.85 minus 34.986, which it's gonna equal to 1/2 times our spring constant times x, which should be something like this. So now I'm gonna have to leave this by itself and divide it. We're gonna do this times 1020, which it's going to be and after getting this, we just have to take the square, which will get us 0.52 and 97 centimeters. I'm sorry, meters. Now for point B, it asks to repeat the previous example, but now there's a constant frictional force posing the motion along the uphill part of the path. So the length of the path is equals to 1.2 meters, and the force equals to 15. So we're gonna take this formula and calculate work done by friction. Which will be 15 times 1.2. So this should be about 15. Now we're just gonna repeat the same process, but take in account this. So kinetic energy again will be equal to gravitational potential energy plus spring plus work done against friction. So this will be 65.85. So we will from here equals to 34. 4.96 plus 1,020 times these 10s plus 18. So now we just gotta solve this, which will be 65.85 equals 52.96 plus 110 times x squared. Now we just gotta 65. X equals 0.342 meters.